All right, in this section, we're going to talk about different types of max and mins and how we determine what types we have. So we've already dealt a lot with local maximums and local minimums. We have been doing that by finding the tangent line and setting it equal to 0 and all of that. But there's a lot more to it than just that. So we've just gotten our feet wet, and now we're going to go a little bit deeper with it. So local maxes, this definition that's given right here, I'm sure you look at and you go, not quite sure what's going on. It's just saying that you have a local max when the y value for a particular x value is the highest over an interval. So in other words, it's higher than anything to its left, it's higher than anything to its right. So when we have that local max, when we have that point that's higher than anybody else to the left or to the right of it. And same thing with local min. We have that local min, we have that point that's lower than everybody else to the left and right of it. But now you can have multiple max and mins, because like if I would finish this graph, it could come up here, it could come down here. That would be another local max, this would be a local min, and so on. So it's like taking a picture and just asking yourself who is the highest part in that picture. But then, in addition to that, making sure that it's the highest part in the picture, but it's the highest part like to the left and to the right as well. Now the key with local max and minimums is that they cannot occur at the endpoints, because it makes sense if it has to be the highest point to the left and to the right, or the lowest point to the left and to the right have to be higher or lower than it. Well, then it can't be an endpoint, because then you're missing either the left or the right side. So then we have absolute maximums and minimums. Absolute maximums and minimums can be endpoints, but they have to be defined. So it has to be defined, and it is the absolute greatest. So like when we talked about local max and mins, we can have all these different maxes and all these different mins, but for absolute there is one, unless that absolute occurs over and over and over again, or occurs twice, whatever. But there can be more than one as long as it's the exact same value. These don't have to be the same value. They just have to be the highest point in that picture, in that little subinterval. Okay, so again, the big difference is local max, local mins. There are many of them oftentimes in a graph. They cannot occur at an endpoint. Absolute max or min is the very highest point on the curve, and it can occur at an endpoint, but it must be defined so it cannot be infinity or negative infinity. All right, I'm going to go ahead and just graph a function so that we can just kind of look at it. So let's say that this is our function. Then let's just take a look at what happens here. What do we have going on? So it looks like this right here would be a local maximum. Like at this highest point, that would be a local maximum. And it looks like that's the only local maximum that I have. But then I have two local minimums. So I've got this local minimum here and this local minimum here. Now, the question is, who's the absolute? Well, who is the lowest point in the entire curve? Wouldn't it be the same absolute minimum would be that local minimum as well. However, because we can include endpoints for absolutes, this one will not be the highest absolute. It won't be the absolute maximum. This point will be, because it's okay to include the endpoints. All right, and then we have some non-examples. So I'm going to just draw you some pictures or some graphs that won't have any of these. So let's say I start right here and I go up, but I have an open circle. Then I'm going to come down here at that same point, and I'm going to go down with an open circle. So this function does not have locals or absolutes because they are not defined. And even though, like in the picture, technically this guy would be a highest point, it's not the highest on the left and the right, only the highest coming from the right, so therefore it can't be a local. So that one does not satisfy any of those. And just another quick example. So if I just start here and make that an asymptote there, that also is not going to satisfy any of these, because the lowest point is undefined and the highest point is infinity. And we don't have any other little ups and downs throughout the curve. So there are no locals, there are no absolutes, And those are cases where we do not have any of the four. All right, so that brings us to Fermat's theorem. Basically, it just says that if we have a local maximum or minimum, so if we have a local, then we know, and if the derivative exists, then we know that the derivative must be 0. And that's just kind of a no-brainer. If you think about like the graphs that we've been dealing with thus far, you know, if you would just draw something like that, it makes sense because wherever I have a local max or min, so like here's a local max, well, its derivative is 0. Here's a local min, its derivative is 0, and so on. And we've been seeing that over and over again. But now, next, it says, as I stated there, the converse is not always true. So, in other words, we can have a derivative equal to 0, and so therefore the derivative exists, but it is not a local max or minimum. I would challenge you to pause the tape right now and see if you can come up with one on your own before looking at the non-example. All right, so I don't know if you were successful, but for my non-example, I am just going to pick a straight horizontal line. Let's call it y equals 5. We'll say that this has a height of 5 on the y-axis. If y equals 5, then technically every single one of these points has a slope of 0, but it is not the highest point or the lowest point on any interval. It is the same as all the others. So again, in order to be a local max or minimum, you have to be careful because to the left and right must be below or be above for it, on both sides have to be the same for it to be a local max or a local min. We are eventually going to combine what we did in section 4.1, the related rates, with critical numbers so that we can do optimization problems a little more effectively. So I want you to take a look at this, and basically you have this in your notes already, so I just want you to read through this part and make sure that you kind of understand what it's saying. And I gave you a little better description in your notes than what I have here. So these are just the definitions. So a number C in the domain of F such that f prime of C equals 0, f prime of C does not exist, and then if f has a local max or min at C, then C is a critical number. So in other words, we want to know where is f prime equal to 0, and where is f prime not defined? Not f, but where is f prime not defined? All right, and then in order, we are going to use this concept. We have actually been doing local max and mins for a long time. We're going to use this concept, though, combined with the 3 steps below here. These 3 right here, these 3 right here, in order to determine absolute max and mins. So the first thing that it tells us to do here is first, find the values of f at the critical numbers. So our first thing we have to do is find critical numbers, and then find the values at the critical numbers. And then our second thing is find the values at the endpoints of our interval. And now if the interval is from -infinity to infinity, there are not going to be endpoints, so we don't need to worry about values. And then our third thing is just interpret the answers from 1 and 2. So whoever has the highest y value is the absolute max. Whoever has the lowest y value is the absolute min. All right, let's do an example. All right, so for this example, I'm asking you to sketch this graph. I thought we should review piecewise functions since those tend to still be kind of an issue for us. So I'm going to ask you to graph it and then find the absolute value, find the absolute max and absolute min based off the graph. So looking at this, it says, and sorry, that's not supposed to be a triangle, it's supposed to be a less than symbol, but it says on this that our first function is defined from -2, including -2, all the way up to 0, but not including 0. When I look at our first function, I see a parabola. I know that it is opening down, and I know that it has been shifted up 4 based on the subtraction sign in front of the x squared and the 4 out front. So starting at -2, if I plug -2 into 4 minus x squared, I get a 0 value. So I'm going to go ahead and put a point there because I know that it's filled in, it exists. And then I know that, like I said, there's a parabola all the way up to 4, but it does not include 4. All right, and then if I look at the second graph, the second function tells me that it's 2x minus 1. That's a linear function. It says it's defined from 0 to 2, and it includes both. So in other words, it's got a y-intercept of -1. So I'm going to start there, and that's defined there. And then it says it has a slope of 2. So up 2 over 1, up 2 over 1. And so then I'm going to go ahead and just connect those points. And again, it is defined at both endpoints. So looking at this function, we have to ask ourselves, do we have any absolute max or mins? When I look at this, I notice the very highest point would be this one right here, but it is undefined. Since it is undefined, there is no absolute max because the absolute max value is undefined. But now we can go ask ourselves, is there an absolute min? Well, the lowest point that I'm seeing is this one right here, and it happens to be defined. In fact, it is f of 0 equals -1. So f of 0 equals -1 is an absolute minimum for this function. All right, our next example asks us to find the critical numbers for this function, this position function. And just a reminder, the critical numbers are the numbers where f prime equals 0. So we're going to do that first, find f prime set equal to 0, and wherever f prime is not defined. So taking a look at this function, if we do f prime, in this case s prime, or velocity, would equal 12t cubed plus 12t squared minus 12t. So if I set that equal to 0, so if I do v of t equals 0, then I would have 0 equals, I'm going to go ahead and factor out a 12t, so it'll be t squared plus t minus 1. All right, we know the endpoints for this are going to be negative infinity and infinity, so we don't need to worry about those. We also know that the domain is all reals because it's a polynomial function, so all we have to worry about is where f prime is equal to 0, which in this case is velocity equal to 0. So at this point, just looking at this, I know that happens when t equals 0 from our first factor, and then I got to figure out where this one would be equal to 0. And now I can't do this one without either polysimults on my calculator or using the quadratic formula. I'm going to go ahead and just use the quadratic formula. So it'll be the opposite of b plus or minus the square root of b squared minus 4 times a times c. And that's all over 2 times a. Now if I reduce that down, I just get -1 plus or minus the square root of 5 over 2. So it looks like my critical numbers are going to be when t equals 0, when t equals -1 plus square roots of 5 over 2, and when t equals -1 minus square roots of 5 over 2. So those are my 3 critical numbers. And again, I don't need to worry about when the derivative is not defined because the derivative is a polynomial function. So we know that the derivative is defined. Its domain is all reals. All right, we have yet one more example and then we'll be done. All right, so we are supposed to determine the absolute max and absolute min for this function on a given interval. So our very first thing that we need to do is we need to find the derivative because we found that in order to do this, we first find our critical numbers. Our critical numbers, again, are wherever f prime equals 0 or f prime is not defined. So our first step would simply be to find f prime. All right, so looking at this one, for f prime, I notice that we have 2 different functions being multiplied together. So I'm going to use the product rule, and just a reminder, that's f prime times g equals plus g prime times f. All right, so f prime would be 1 times g is 4 minus t squared plus f times g prime. And I know g prime is going to be, just because that's the square root of something, I know its derivative is going to be 1 over 2 square roots of it, because that's what we do when we have a square root. But then I have to multiply by the derivative of the inside function. And the derivative of 4 minus t squared happens to be -2t. All right, I'm going to go ahead and do some simplifying here, and then I'm going to interpret all of this. So we can reduce these 2's. And we would have f prime of t equals the square root of 4 minus t squared plus, and then I would have t squared over square roots of 4 minus t squared. Now again, I want to know when this, well, first of all, I need to check the domain of f prime, so I might do that first. And I notice that we do have a domain issue because this guy appears twice. We know we can't square root a negative, but because it also appears in the denominator, we also can't let it equal 0. So I'm going to figure out where 4 minus t squared is greater than 0. And it happens to be greater than 0 for the absolute value of t is less than 2. So that means between -2 and 2, not including them, it happens to be, or that happens to be defined. So therefore, where is f prime not defined? Well, it's not defined at -2 and outside, and not defined at 2 and outside. Well, now if I go back up here to the interval, the only one we need to concern ourselves with is 2. So the only thing I care about with f prime not being defined is the 2, because -2 is not in the domain of the interval, or not on the interval. And we were already actually going to check 2 because it's the endpoint of the interval. So that's already taken care of. But we needed to make sure that we covered the domain. So now our next thing, once we get this last part here, then we will be ready to go ahead and determine who has the highest and who has the lowest y values. Okay, so we want to know where f prime is equal to 0. All right, so I'm going to go ahead and just set f prime equal to 0. All right, if I set that equal to 0, there are a couple of different things that I can do here. You know what I just noticed? I dropped a negative symbol all the way down. This should have a negative there because there was a negative here. And so that should have been minus there. That's why. Okay, so now we should be clear. So that's why this is a minus sign right here, because that was a negative up there. All right, so I'm going to go ahead and move this up a little bit so I've got a little more room to work with. And I would have, if I move this over to the other side, I'd have t squared over square roots of 4 minus t squared equal to square roots of 4 minus t squared. Now I'm going to go ahead and multiply both sides by this guy right here. So my left side will become t squared, and my right side, that's basically squaring a square root. So it'll just become 4 minus t squared. All right, now I'm going to add t squared to both sides. So I get 2t squared equals 4. Divide both sides by 2. I get t squared equals 2. So I then know that my answer would be t equals plus or minus the square root of 2. All right, and again, now I ask myself, my interval was -1 to 2. Are both these t values in that interval? And the answer is no. Negative square root of 2 is outside of -1, 2. So the only one we have to concern ourselves with in this case is the positive square root of 2. So it looks like the three numbers that we need to check are when let's see, t equals -1, because that's an endpoint. When t equals square root of 2, because that's in the interval, and that was one of the 0 tangents. And at 2, and that happened to be the end point of the interval, so we check it anyway, but it also happened to be one of the places that our derivative was not defined. All right, so we simply, to finish this up, is we simply just say then f of -1, f of square roots of 2, and f of 2. We plug those into the original function, and we get negative square roots of 3, we get 2, and we get 0. All right, this guy is our lowest y value, so he will be our absolute min. And this guy is the highest y value, so he will be the absolute max. All right, come see me if you need to get some help.